Good day, grade 11s. I trust you're all doing well today. We're going to focus for this lesson on electromagnetism. Electromagnetism is the study of the relationship between an electrical current and the magnetic field that forms around the current-carrying conductor. Now, during this study, we build up to what we're going to do in matric, where we start working with electrical motors and electrical generators. So let's have a look at our key concepts. The key concepts we're going to be focusing on for this section is the relationship between a magnetic field and the straight current carrying conductor, as well as what happens with a magnetic field that is formed inside a single loop or a solenoid. From there, we're going to briefly look at electromagnetic induction and then electromagnetic induction by electrical methods. That would be our study on transformers. We're going to have a quick squiz at charged particles moving through a magnetic field, and from there on we're going to look at our calculations for this section. Electromagnetism, as I said, is the study of the properties and the relationship between electrical currents and magnetic fields. All right, so electromagnetism is the study between the electrical current and the magnetic field. Scientists were intrigued by the relationship between the two. One such a scientist was Hans Christian Ørsted, who discovered the relationship between an electrical current and a magnetic field whilst preparing for a lecture. We see over here that an electrical current is the rate at which charge flows through a circuit. Remember that the term rate refers to any quantity being divided by time. So over here we are looking at the amount of charge that is divided by time. In an electrical current, we look at the charges that move about. Now, for different types of conductors, we will look at different charge particles. When we deal with metals, the charge particles will be the electrons that move around in the conductor. In an electrolyte, these would be the negative and the positive ions or charges that we have in a solution. Remember that an electrolyte over here refers to an aqueous solution that we deal with in chemistry, and that these negative and positive charges would be your negative ions, known as anions, and the positive charges would refer to the positive cations that would move around in such a solution. When a charge travels through a current-carrying conductor, we will notice that as the conductor carries the charge, that a magnetic field will develop around this conductor. And it is going to be this magnetic field that we are going to concentrate on. If we look at the magnetic field lines that are developed around such a current-carrying conductor, we will notice that these field lines move in a specific direction. The rule that will help us to determine the direction in which these field lines move is known as the right-hand rule. Important thing to remember over here is that the field lines for the magnetic field is always at right angles or 90-degree angles with the current-carrying conducting wire that we work with. If we use our right hand and we focus on the current-carrying conductor, say for instance this is our current-carrying conductor and the current flows from the top to the bottom. If I take my right hand and I point my thumb towards the direction in which the current flows in my pen, as such, your fingers would curl around the pen in a natural way. The direction in which your fingers curl around this conductor would be the direction in which your magnetic field lines move around this current-carrying conductor. Let's look at the diagram representation over here. Remember, when a current moves towards you, we look at it as a single dot, as indicated over here. And when the current moves away from you, we indicate it by using a cross or an X to indicate that the current is moving away from you. So if we look at this one, the X indicates that the current is moving away from the observer or into the page, so to speak. If my thumb points in the direction in which the current is moving, the natural curl of my fingers would be in a clockwise direction. We indicate this clockwise direction on these coils with arrowheads. If they go down in the one side, they would go up on the other end. That would indicate the direction in which the magnetic field moves around this specific conductor. On the other side, the current is coming towards the observer or out of the page, and that is indicated over there by the dot. If the current is coming towards the observer, be sure to point the thumb towards yourself and let your fingers curl naturally around your thumb. The natural direction in which your fingers curl in this case is an anti-clockwise direction. That means it would go down at this end and they would move up at that end, indicating an anti-clockwise rotation. There we go. That is how we're going to indicate the direction in which the magnetic field lines move around a current carrying conducting wire. When we start working with a coil or a solenoid, we no longer have single pieces of wire that travel and carry charges in one direction. We now take the wire and we turn it into a loop, which means that your current is now going to follow a circular path. When the current follows this circular path, it has certain effect on the magnetic field that is created around the current carrying conductor. If we look at the diagram over here, the gray line over here would indicate the direction in which my current is moving. So if my current is moving from right to left, it would be completing its path in an anti-clockwise direction as such. If we follow the rules of the magnetic field using our right-hand rule over here, we would see that the current goes up in that direction and the magnetic field would rotate around it. Indicate the direction in which your magnetic field rotates around it, and we are going to do the same on the other side. The current comes up over here, it is going to flow and go into the page on that side. Look at the direction which your fingers curl, and we will see that on this side, our magnetic field moves in a clockwise direction around my current carrying conductor. If I were to go and extend these field lines, I would pretty soon notice that it creates a magnetic field very similar to that of a bar magnet. If this would be my bar magnet, indicating north and south, we would notice that the magnetic field moves from the North Pole to the South Pole on the outside of my magnet. Over here we have exactly the same. Your magnetic field comes in and it moves out onto that side where it completes a circular path. And over here we notice the same thing, that it comes in and it completes a circular path. Where the current goes, or where the magnetic field goes out at the one end and comes in on the opposite end, goes out at the one end, comes in at the opposite end. The area where it goes out is where your North Pole is situated. The area where the magnetic field comes back into the coil over here would be our South Pole. Please note that for the coil that we have over here, the north and the south completes a circular path. So where on a bar magnet we notice that the magnetic field moves from on the outside only, we notice with these coils that the magnetic field completes the circular path on the inside. And on the inside between the two wires, the magnetic field runs from south to north. But on the outside, it still runs from north to south, as with a conventional bar magnet. It is important that you guys remember that and you don't swap them around. Now the pattern shows that when it is on a flat disc as I indicated above here, it is going to represent the exact magnetic field lines that we would get in a bar magnet. Also remember that on the inside of the circle, we are going to have a stronger magnetic field. The reason for this is because the magnetic field lines are closer to each other. It also indicates that the magnetic field over there would be stronger. The stronger the field, the closer the lines are together, and that would cause an increase in the magnetic flux. Now remember that the word magnetic flux is another term that we use to refer to the magnetic field that we have around a magnet, or in this case, a current carrying conducting coil. On the inside of the coil, if we go and we look, let's just redraw that very quickly for you guys. On the inside over here, we would notice that these lines get fairly close together. And if I have more than one coil around each other over here, these field lines would make almost a parallel line, which allows the magnetic field to run through there. Remember, as with static electricity, when we have parallel lines running, it is an indication of a uniform field. So over here in the center of our coil, where the lines lie parallel next to each other, it is an indication that we have a fairly uniform magnetic field inside the coil that we deal with. Remember, when we've got such a diagram where we've got magnetic fields around current carrying conducting wires, you are still allowed or still able to use the right-hand rule to indicate the flow of the magnetic field. Whether it is multiple coils or just a single point indicating the flow of charge, around each one of these you can still use the right-hand rule indicating the magnetic field. Just a reminder that the field lines form closed loops, and there are closed circles that lie around the coil for the current carrying conductor. And once we see that, we would be able to go and determine the north and the south pole of such a current carrying conducting coil. When we have multiple loops, those multiple loops are known as a solenoid. Now previously we had one single loop where we had current coming in and going out, and that made a loop. Over here you will notice that our current comes in on this side and it forms a coil. And this coil represents multiple loops that carry current over here. Now each one of these loops is a representation of a setup like this, and around each section of coil where we've got a current carrying conductor going in there, there will be a magnetic field around it that would indicate to us the direction in which our field moves around here. So when we've got multiple coils, it now becomes more visible that we've got a coil or a magnetic field around here that represents that of a normal bar magnet. Notice over here how they are close together near the ends, and they move further away from each other as we move out from the coil. I would just like to draw your attention to these magnetic field lines that we find inside the solenoid. You will notice that these lines lie very close to each other, but they never actually cross. Remember what I said previously, when these lines are so close to each other that they virtually become parallel, it is an indication of a uniform field that we find between these two coils. Also notice the arrows that indicate the direction in which your magnetic field flows. On the outside of your solenoid, the magnetic field lines flow from the top all the way around to the bottom. From the top all the way around to the bottom, with the arrow indicating the direction in which it moves. Remember, on a bar magnet, the magnetic field lines move from north to south. And in this case, if we follow the flow of those magnetic field lines, we would notice that our north pole is situated at the top, with our south pole situated down here at the bottom, as indicated on your sketch. Also remember that within a solenoid, the circular path is completed. This circle on the outside runs all the way through on the inside, and it completes the path, which means that on the inside of my coil, my magnetic field runs from south to north, but it is on the outside that it follows the traditional north to south. Electromagnets and electromagnetic material. An electromagnet refers to any current carrying conducting wire that has a magnetic field around it. Now, once we have this current carrying conducting wire and we now put it around an object that is magnetic as well, we enhance the magnetic property of such an electromagnet. Not all substances can be magnetized. If you go back to your studies that we did in grade 10, you would remember that we have three naturally occurring magnetic materials: iron, cobalt, and nickel. Whenever we make an alloy or a mixture of metals containing any of these three metals in that substance, that specific metal will also have magnetic properties. Now, in our study over here, we will see that if we use a substance like iron, it will become very easily magnetized, but it will also demagnetize very easily. The word demagnetize means that it would lose its magnetic properties the moment we switch the current off. Remember, as long as the charged particles move through the current carrying conducting wire, there will be a magnetic field. Once I stop these charged particles from moving around, either removing them from the energy source or by opening up the switch in my circuit, the charges will no longer move and my magnetic field will cease to exist. When we deal with other substances like steel that are referred to as hard iron alloys, it becomes more difficult to magnetize them, and they retain their magnetism after the current has been removed. In the industry, this is used to make permanent magnets that we then use as fridge magnets, in our cell phones, in computers, all sorts of devices that depend on these magnets. Just a couple of things to remember that we can do to enhance or strengthen the magnetic field of such an electromagnet. That would be by increasing the current, by increasing the number of turns, or by changing the substance that we use inside the core. These three would therefore determine the strength of the electromagnet that we are working with. Let's look at some uses of electromagnets in our everyday life. They come in a variety of shapes and sizes, which allow us to use these electromagnets for a variety of purposes. They can be used in small capacities, huge capacities, lifting up cars, moving huge chunks of scrap metal around, or to the small extent where they power your cell phone, where there is an electromagnet involved. Lifting magnets, as I mentioned, in scrapyards, electrical bells, relays, loudspeakers, telephone receivers, tape and video recorders, as well as electrical motors. Remember, next year we are going to focus a lot on those electrical motors in the studies in grade 12. Let's look at our electromagnetic induction. Michael Faraday did quite a lot of research into electricity, and he was searching for a perpetual energy source that would not have to be regenerated. And that led him to working with electricity as well as magnets. During his studies, he discovered that if I have a current carrying conducting coil through which my current moves, I would be able to generate a magnetic field. He reasoned that if I have a solenoid or a coil without current running through it, and I would bring a magnetic field into that current carrying conductor, that it would theoretically produce a charge moving through that coil. He then set about to do the studies to prove this theory of his, and that is where we are today with Faraday's law. If we have a magnetic field or a magnet that is moved relative to a coil, an electrical current will be induced in the circuit, and this would be referred to as electromagnetic induction. This would refer to magnetical energy being transferred into electrical energy. This results in an EMF that is produced, and this causes the flow of charge or current in a closed circuit. This EMF we are talking about refers to your potential difference measured in volts, and the flow of current that we have over here refers to your current measured in ampere. The induced current flows only for a short period of time. As long as my magnetic field moves relative to the solenoid, there will be charge. Once the magnetic field stops moving, the charge will also stop moving. If my fingers were to represent the solenoid running across over here, and the pen would be the magnet, the moment I insert the magnet into my coil, it would cause the charged particles over here to move. The movement of the charged particles through this coil would therefore show, if I had an ammeter, it would indicate the flow of charge over here. Once I keep my magnet still, the charged particles will stop moving. If I remove the magnet out of the coil, it would set the charged particles into motion again. Now notice each time I insert the magnet or I remove the magnet, this movement is in a different direction. The result of this magnet moving in or out of the coil would result in charge moving in different directions. So the charge that is generated would be an alternating current that we deal with. The strength of such an induced current depends on three things: the speed with which the magnet is moved in or out of the coil, the magnetic flux, in other words, the strength of my magnetic field, as well as the number of turns that I have on the solenoid. Let's just linger on the number of turns. Remember, if I have more turns in my solenoid, it means that more charged particles would be activated or set into motion by my magnet that is pushed into the coil. So more turns means more charged particles that are exposed to the magnetic field, and therefore we will have more or a greater current moving from there. Now the magnetic flux linkage is denoted by the symbol, and we use the following formula to calculate the magnetic flux linkage. B stands for the magnetic field strength, which is measured in Tesla. And this is named after the American scientist Nikola Tesla. And the area over here, which is measured in meters squared. So if I put the two together, let's just have a look over there. Your magnetic flux linkage would therefore have the unit of Tesla meters squared, where Tesla comes from the B being measured in Tesla and A measured in meters squared. Any change in the magnetic flux will induce an EMF that can be measured in potential difference, and this is referred to as electromagnetic induction. Faraday's law of electromagnetic induction states that the induced EMF, or the produced current potential difference, is directly proportional to the change in the flux and inversely proportional to the change in time. The formula for this is denoted over here. Epsilon, which refers to the induced EMF, is inversely proportional to the directly proportional to the magnetic change in flux and inversely proportional to the change in time. The N over here would represent the number of coils. Remember, we just previously stated that an increase in the number of coils would result in an increase in the flow of charge, which we have over here as the EMF that is produced. Electromagnetic induction and Lenz's law. Now, Lenz's law refers to the direction in which the charge would flow if I induce the current over here. For us to investigate Lenz's law, we need a coil, conducting wires, and a galvanometer as well as a bar magnet. The purpose of the galvanometer is to indicate the direction in which your charge flows. So this little symbol over here would represent the galvanometer. If you pay attention to the sketch, you would notice that we have a north pole of a bar magnet that is being pushed into a coil. The coil does not carry charge at the moment, but as soon as I insert the magnet into the coil, this north pole causes or creates a north pole on my solenoid. These two north poles oppose each other, which means that upon insertion of the bar magnet, the coil will try and push the magnet out. That would create a flow of charge particles in the opposite direction. If I try and remove the bar magnet from the coil over here, there's your north pole. The change in direction of my magnetic insertion would result in a south pole that is created at the same end of my solenoid. These two magnetic poles now attract each other, which means that again the direction of my current that is induced over here would change. If you compare the two sketches, we need to look at the following. Remember that for the bar magnet, for each one of these, I'm inserting the north pole into my solenoid or my coil. Upon insertion, when my bar magnet moves into the coil, it creates a north pole at the end of the solenoid where my magnet is inserted. These two north poles will oppose each other, creating the flow of charge in a direction. When I remove the bar magnet, it is going to create a magnetic pole opposite to that of my bar magnet. This now attracts the bar magnet back to the coil and causes my current to flow in the opposite direction. Your galvanometer would indicate this by the needle pointing in the direction in which the current is flowing. The purpose of the galvanometer is not to show a measurement like an ammeter or a voltmeter. The galvanometer has a needle that can point either left or right, indicating the direction in which the current is flowing. Although it is calibrated, the calibration is there to only indicate the magnitude of the flow that we have over there. There is no unit of measurement when we work with a galvanometer. If the north pole approaches, it is going to be pushed out, and when I retract it, it is going to be attracted again by the oppositely created south pole inside my solenoid. Electromagnetic induction by use of electrical methods refers to electrical current passing through a conductor. Now, depending on which type of current we're using, either direct or alternating current is going to determine the magnetic field that is generated. If you have a direct current, your current would flow in one direction only. If your current moves in one direction alone, it would create a magnetic field that stays fixed. So if my current was moving around, I would have a north pole and a south pole that stays at the same end of my electromagnet. If you have alternating current, the direction in which the current moves is going to change at regular intervals. This means that the magnetic field around your coil is also going to change direction at regular intervals. This has certain advantages for us. Instead of having someone sitting inside an electrical motor changing the direction of your magnetic field all the time by inserting and removing a little magnet over there, we use the electrical field that is created by the charge as it changes direction to change the magnetic field around that current carrying conductor. A regular change of charge means a regular change of a magnetic field. This change of magnetic field can then be used to induce a magnetic field in a coil that is brought close to this, which we refer to as a secondary coil. When the one coil induces a magnetic field onto another coil, it is called mutual induction. When studying this, we are going to focus on transformers. If you go through the text, we will notice over here that the coil that has the deliberate change in current is referred to as the primary coil, and the one that experiences the induced current is called the secondary coil. Let's just have a quick look at the setup over here. If this was my energy source, and it is an alternating current energy source, and this was attached to a coil, this coil would create a magnetic field around it. If I then brought a second coil close to this one and I attach it to a galvanometer, the moment my charged particles start moving through my coil over here, the arrows indicating that it can go in different directions, it is going to create a magnetic field around this coil over here. This magnetic field will change from north to south at regular intervals as my alternating current changes direction. This magnetic field would then cut through the coil that I have over here, and as the magnetic field changes its direction, it is going to create a current inside the secondary coil that I have over here, and my little galvanometer would indicate the direction in which the charge flows. Remember, alternating current, it means that the current can move in any direction. It is generally indicated in a circuit by the following picture: circular component with a sinus wave in there. That would indicate an alternating current. Or alternatively, they could just insert there that it is a power source. This would be a very, very simple transformer. Now, the induced potential difference in the secondary coil can be created to be higher or lower, and that depends on the potential difference or the alternating current that comes from your primary coil, and it also depends on the number of turns that we have on our primary and our secondary coil. Let's investigate that further. The principle of a transformer indicates that the number of turns in the primary coil and the secondary coil, if they were to be equal, the potential difference would stay exactly the same across the primary and the secondary coil. So if they have the same number of turns, it is going to result in an equal EMF for both of them. Now, if the number of turns in the secondary coil is going to be greater than that of the primary coil, so N denoting the number of turns, if it is greater in my secondary coil than it is in my primary coil, we refer to this as a step-up transformer. Step-up transformers allow us to increase the potential difference, or the EMF, that we have in our transformer. If we go and we take the number of turns for our secondary coil and we reduce it so it now becomes less, so they become less than the number of turns for my primary coils, I am going to decrease the EMF that I have in such a transformer. Now, you would notice that if I am able to increase or decrease the EMF, it's going to have certain advantages. If I work with an appliance such as my television set, I need to increase the potential difference so that my TV can work. To successfully work with my television set, I need a step-up transformer to increase the EMF from our mains from 240 roundabout to the 25,000 volts that is required to run the TV. But if I want to charge my cell phone, I'm going to need to step down the EMF significantly from the 240 volts that comes from the mains to approximately 9 volts so that I can charge my cell phone. A further alteration that we need to do there is, remember that a cell phone works on direct current. Main electricity that comes from your mains is alternating current. So together with a transformer that reduces the potential difference, we also use a rectifier that causes the direction or the charge to flow in one direction only, so that you can charge your cell phone from the main socket, as we do on a daily basis. Now, the size of the induced EMF depends on the number of turns that we have in the two coils, and it leads to the following formula. The voltage in the primary coil divided by the voltage in the secondary coil. So we are looking at the relationship between the potential difference is equal to the number of turns in my primary over the number of turns in my secondary coil. A quick and easy way for me to remember this is that P lies before S in the alphabet. So P goes on top of my S for my primary and my secondary potential difference, or my primary and my secondary number of coils. In a perfect transformer, the energy supplied to the primary source is drawn from the secondary. In South Africa, we make use of step-up transformers to increase the voltage of the electricity that is generated at power plants, so that the electricity can be transported over long distances along pylon lines to transport the electricity from the power plant to different distribution stations, from where it is sent down to substations into the areas where we live. It is safe to transport electricity at a high voltage and a low current over long distances. Hence the fact that we use step-up transformers and then step-down transformers once we transport the electricity into our suburbs. Charged particles within magnetic fields. Remember that if I have a charged particle that is going to move through a magnetic field, it is going to experience certain forces acting on it. Now, as long as these two forces interact with each other at a 90-degree angle, or they are perpendicular to each other, the force that is experienced by the charged particle will be at its greatest. If the angle changes, the force is going to decrease significantly. And when these two forces are parallel to each other, in other words, the charged particle moves in line with the magnetic field or in a different direction, as long as they are in line and parallel, the effect of the force is going to be zero. You are going to use this knowledge again next year when we deal with electrical motors and electrical dynamos. But for now, let's look at what happens to that charged particle within a magnetic field. Remember earlier on we said that a cross indicates the charge moving into the page or away from the observer, and a dot means that it is moving towards you. Now this also allows us to work with magnetic fields. Now over here, the crosses indicate to us that the magnetic field is moving into the page or away from us as the observers. If Q is my charged particle that carries a positive charge, and I were to go and accelerate this charged particle with a certain velocity through the field, this charged particle, the moment it enters the field, will experience a force that is going to cause it to move in a different direction. So as the charged particle comes into this field, instead of moving straight across, it will experience a force that is going to push it up, and it is going to deviate and move away towards the top of our sketch over here. If we take our right hand and we use our fingers to point in the direction in which the magnetic field is pointing. So our fingers, these four, would point in the same direction as the magnetic field. Allow your thumb to point in the direction in which the charged particle is experiencing an acceleration or the velocity. So your charged particle is moving towards the right, magnetic field is moving towards into the page, and your palm would therefore indicate the direction in which the force is experienced. Let's just run over that again. Your hand, the fingers of your hand point into the magnetic field. Your thumb is going to point in the direction in which your charged particle is experiencing the acceleration or in which it's moving. The palm of your hand would therefore point in the direction in which the charged particle will experience a force. This force will push the charged particle into a different path, and that is where it's going to move towards. Now the relationship over here can be denoted by the following formula. Remember that force is measured in Newton, charge is measured in Coulomb, velocity measured in meters per second, and B, which stands for your magnetic field strength, is measured in Tesla. Question 1. A piece of copper wire is clamped into a vertical position. When connected to a battery in a closed circuit, the direction of the current is downwards. Draw a sketch to show the current and the magnetic field when viewed from above the conductor. Remember, when it comes to questions like this, it is always good to have a picture in your mind of what you are dealing with. So if we quickly go and draw our retort stand with our clamp over here, our current carrying conducting wire, which I'll do in pink for us, will be hanging from the top all the way down to the bottom. If I now go and I connect this to my power source, the question tells us that the charge or the current flows downward as my current carrying conductor or my copper wire is hanging there. That would indicate that the charge is going to move in this direction. With that picture in mind, let's now go and answer the question. They want us to show the current as well as the magnetic field when we are viewing this from the top. If I'm looking at this picture from the top, I would be noticing the following. I would only look at my conductor as a little dot and open space around it. Now transfer this little dot into the terms that we have for the charge. Remember, when the charge is moving away from you, you are going to use a cross, which would represent the current carrying conductor. And now let's look at the magnetic field. Remember that the magnetic field would be formed in concentric circles around my current carrying conductor. Go and draw a couple of concentric circles and then go and apply your right-hand rule. The charge is moving away from me or into the page, so my thumb is going to point in that direction, and my fingers will curl in a natural direction around my thumb. This direction is in a clockwise motion, so I go and I use my arrows to indicate the direction in which it is flowing. So there we've got it, very simple. There's my current indicated with a cross. The current is moving away from the observer. That is the eye of the observer. The current is moving away from it, indicated with a cross. You can put that in a circle. And then the magnetic field that is experienced around it, to indicate that, we are going to use the right-hand rule and show the direction which my fingers curl. That was question 1.1. If we use the same setup and we look at it from the side, how would that affect our sketch? Now remember, we'll do the same thing over here. There's your retort stand with your clamp. Here's your current carrying conducting wire hanging down. This is attached to our power source, and the current is going to move in that direction. If I'm looking at it from the side, let's draw our observer over here. I'm going to be looking at it like this. So I would have over here my current carrying conducting wire, and around it I would have a magnetic field. My current is moving from top to bottom, so I use my arrows to indicate the direction in which it would be moving. So to go and indicate the magnetic field line or the magnetic field around it, we're going to use a different color. Remember from the previous sketch, we said that the magnetic field made circles around it where it moved in a clockwise direction. That means that on my left-hand side, my magnetic field would be moving into the page. If anything moves into the page, it is drawn with crosses. As I move further away from my current carrying conductor, I would find that these crosses move further away from each other as my magnetic field decreases. The other end, I find that my magnetic field is coming out of the page, and it would therefore be represented by a series of dots. As we move further away, it is going to move out. You can just complete it and indicate over here how the magnetic field would form around it. You would notice that in one half of my sketch, I indicate that the magnetic field is moving into the page, and the other half is where magnetic field is moving out of the page. So over here, magnetic field into page, magnetic field out of page, and there is my current carrying conducting wire indicating the direction in which my current is moving. This section allows for a lot of nice questions where we have applications, where you're going to have to draw sketches, explain things, explain your sketches, explain the drawings, and explain the theory behind it. So be prepared and make sure that you know your theory really well for this section in order to answer all of those explanations. Question 2. The sketch below shows a circular coil wrapped around a plastic pipe. The coil is connected to a battery in a closed circuit. So if my current comes over here, this is my positive pole, my current is going to move in this direction, and here it goes up and down at the back. So my current is going to move up in front, down at the back. Remember, although we don't see the direction in which my current is flowing at the back, it is still completing that circular path. So that gives us an idea of the direction in which it flows. So at the back over here, once it has finished its coil, the current will move out and go and complete its path. Now they ask us for 2.1 to draw a sketch of the coil when viewed from above. And they want us to clearly show the direction of the current as well as that of the magnetic field. So we are going to be observing this coil from the top to see what is going to happen to it. So let's go and only redraw the section of the coil. Start off with your plastic pipe. It is then easier to go and draw the coil around it. So if it goes up on this side, it's going to come down, and I would have over here my coil moving around, and it's going to go out on that side. Indicate the direction in which your current is flowing, and over here on the coil also indicate the direction in which the current flows on the coil. Comes in, goes up, down at the back, up in front. All right, so that was then the direction. Let's look at the magnetic field. Remember that we use our right-hand solenoid rule, whereby our fingers will point in the direction in which our current is flowing. If I grip onto the solenoid and I extend my thumb is going to indicate my north pole. That is the north pole, this would be the south pole, and the magnetic field that is generated over here would flow from north to south on the outside. And on the inside, I can use a dotted line to indicate that it completes the magnetic field line over here, and on the inside it flows from north to south. It is always a good idea to draw more than one set of magnetic field lines around here. Just remember that these field lines never touch, they never cross, and they extend all the way from your coil to the outside to indicate the magnetic field around it. So there you go. You've got your magnetic coil indicating the flow of my charge. You've got your magnetic field lines that extend around it, indicating where your north pole and where your south pole will be situated for this specific solenoid. Question 2.2. We're going to use exactly the same sketch, and now they want us to draw a sketch of the coil when looking into the coil at the end labeled at X. So if I were looking into this coil from this side, what would my observation be? Let's stick to green for our current. If I look into my coil, there's going to be my plastic pipe. My wire would be wrapped around this pipe. Remember that the current started flowing in from this side. So our current will move in a anti-clockwise direction around the coil. If we now want to look at the magnetic field that we have over here, from our previous sketch, let's just go back to this page. From our previous sketch, you would have noticed that the north pole would have been on the side where X is situated. So if that is my north pole and I'm looking into the pipe, I would experience the magnetic field moving towards me. So if we go and we answer question 2.2, remember that for this sketch, this is going to be my north pole, that is my south pole, and the magnetic field on the outside moves from north to south. But on the inside, the magnetic field is going to move from south to north. So the magnetic field is coming towards me as the observer, and when the magnetic field comes towards us, it is going to use, we're going to use the dots. Remember that these dots are situated fairly close to one another, and again, they're not going to touch. But what happens on the outside of my coil? On the outside of the coil, that is where the magnetic field is moving away from us, where it moves from the North Pole to the South Pole. And we're going to indicate the magnetic field around this coil with a series of crosses. And you could also go and indicate that as I move further away from the cross or from the coil, that these crosses also move further away from each other. All right, quick recap over there. That is the direction in which my current is moving around the coil. On the inside of my coil, the magnetic field is coming towards my observer, and on the outside, my magnetic field is moving away from the observer, from north to south, from south to north. Question 2.3. If this coil has a radius of 3 centimeters, the magnetic field produced is going to be 2,5 Tesla. Calculate the magnetic flux that is inside of the coil. We are going to use the following formula. Your magnetic flux is equal to the strength of the magnetic field multiplied by the area across which this magnetic field is experienced. Remember, we are dealing over here with your pipe. For the area of a circle, we are going to calculate pi r squared. All right. You have to do a couple of conversions over here. So let's start from the top and work our way through all of the necessary calculations. In order for us to calculate the area, we need to convert the radius from centimeters into meters. They tell us that the radius is 3 centimeters. Divide that by 100, and it is going to give us our radius in meters. So that would be 0,03 meters. We're going to use this in our area calculation. So the area of a circle is equal to pi r squared. Remember that pi, or some people refer to p, is a value that is found on your calculator. You can either write the symbol or you could go and write the numerical value. We use it rounded off as 3,1415 multiplied by 0,03, and we're going to square that value. Now let's bring up our calculator. Remember, your calculator is fitted with a value already for pi. So second function, or shift, pi multiplied by, I like to use my brackets, 0.03 square, close brackets, and there we have our answer. You can choose to write this answer in exponential form, or we can go and write it as it is on the calculator, 0,0282. Be careful not to round off too early, as we still need to use that value in a further calculation. Extend the page. That was 0,00282 meters squared. Okay, we are now going to substitute this area into our other calculation. So this is going to be used over here. They tell us that our electromagnetic field is 2,5 Tesla. So that would be our 2,5 multiplied by the value that we calculated just now, which is our 0,00, let's just open space over there, 282. Bring out our calculator again. Previous answer is still over there. We're going to use that answer, multiply that with a 2.5, and we're going to get our new answer, which is 0,00706. your instruction would tell you to round off to 2 decimals, and because we're rounding off to 2 decimals, it would therefore be safer to go and write it in scientific notation. So let's just write the original value, 0,00706. Rounded off would give me 7,06 times 10, and it has moved 1, 2, 3 spaces, times 10 to the power of -3 Tesla meter squared. Okay, that is our final answer. Remember, work out your area first, then substitute the area into your calculation over here and complete the calculation. Let's look at question 2.4. Same diagram, all the information stays the same. They now want to know 2 ways in which the electromagnet can be made stronger. If you remember from our previous text, there were 3 methods that we could have used. So here they ask us to only mention 2. If you mention 3 and the question asks for 2, we're only going to mark the first 2. So answer the question according to what is asked. The first thing we could do is we could increase the current that goes through the circuit. Increase the current that passes through the circuit. And the second one, which is very important, is to increase the number of coils. Also referred to as turns. Now the third one referred to the substance that we put inside. As you would notice over here, this is a hollow pipe. I can't insert anything in there. So the third one, where they say that the type of substance that we insert into the coil would be the one that is going to increase the electromagnetic strength over there, is not really relevant to this particular question. Although if you stated that, the marker would mark it correct for you. Question 3. You are given a coil, connecting wires, a bar magnet and a galvanometer. Describe how you would use this apparatus to verify Lenz's law. Now, I don't know about you guys, but I find it a lot easier to describe something to someone if I've got a picture in my head or on a piece of paper that I can use for my explanation. If I had to do this question in an exam, I would start off by doing a sketch of how I'm going to set up this apparatus and use that sketch to explain exactly what I'm doing over here to determine Lenz's law. So let's start off with your sketch. They tell us that we are given a coil, so go and draw your coil. We have got connecting wires. So here are our connecting wires. They are connected to a galvanometer. And we are given a bar magnet. Let's make the magnet white. All right. Now, if this was our first slide, we know that if the magnet moves into the coil, it is going to create a north pole over here, which means that they would oppose each other. If it moves in this direction, we're going to use that one. Our magnetic field moves in that direction, and we would notice that our electrons or our charged particles would therefore be moving away from it, and they would move in that direction, causing my galvanometer to swing out over here. If you get stuck over here and you're not sure about the direction in which the charge flows, it would suffice if you only indicate the sketch where you've got the coil, the connecting wires, the galvanometer and the bar magnet, and indicate the direction in which the bar magnet is moving, indicate the two magnetic poles that are created, and do a second sketch where you would indicate that it is moving in a different direction. So in our second sketch, we would go and we would draw the bar magnet again. We would go and indicate the coil. We would have our connecting wires and our galvanometer. And now the important thing over here is to indicate that the magnet itself is moving in the opposite direction and that it would now generate a south pole over there. Okay, that would be enough for us for the sketch. Now we are going to describe and answer the question on how we would use this apparatus to verify Lenz's law. Point form works for me. You might want to write a sentence. So I would start off by saying, set up the apparatus as indicated in the diagrams. What did we do secondly? Second step, we took the magnet and we started moving it into the coil. So we would mention over here, insert the magnet into the coil and observe the motion or the movement on the galvanometer. An observation that you should be making, remember that the charges will only move once the magnetic field is moving or while the magnetic field is moving. As long as your magnetic field is stationary, the charges will not move. So you would have to include over here your observation that when the magnet is stationary, no charges will be moving, and therefore the galvanometer would go back to its original position. When the magnet is stationary, the charges do not move and the galvanometer returns to its original position. Okay, last observation over here. If I now retract the magnet and I pull it out of the coil, it is going to induce a current yet again, but the magnetic pole that is going to be created is going to be opposite to what it was with the insertion, and that means that my charges will move in the opposite direction. So once we do this, when we remove the magnetic or the magnet over there, when we remove the magnet from the coil, the magnetic pole that is induced is opposite to the magnetic pole of the bar magnet. The charge that is generated moves in the opposite direction and the needle of the galvanometer moves in the opposite direction. All right, there we go. Little bit of a lengthy answer, but as I said, strategy, go and draw the sketch. The sketch will help you to use your define your explanation, to set your explanation out nicely. Point form is always a good idea. It is a structured way of giving your answer, and the person marking the exam paper can clearly see exactly what thoughts were going through your head as they go through your answers over there. Let's look at the following question. Question 4. A circular coil of wire with a radius of 2 centimeters has 80 turns and is connected to a galvanometer in a closed circuit. A magnet creating a magnetic field of 50 millitesla is pulled quickly from the inside of the coil until it is far enough so that the effect of the field is 0. The time taken for the magnet to move is 0.2 seconds. Calculate the reading on the galvanometer. Now there's a lot of information given to us over here. For us, the difficult part is now going to be to break up the information and to use it into the correct sections. Again, they give us the radius of our coil, our circle that we are dealing with. So that tells us that we're going to have to calculate area. So we're going to start with that section first. We're going to move it on and bring it into the rest of our calculations. Also remember with this one, very important that we work with the correct SI units. I see that yet again they have given us our information or our radius over there in centimeters. So let's start off. Our radius is given to us as 2 centimeters. To convert from centimeters into meters, we divide it by 100, and that is going to give us 0.02 meters. Okay. They tell us it is a circular coil of wire, so our area would be the area of a circle, and that is going to be pi r squared. Pi 3,1415 multiplied by your radius, which is squared 0.02, square that. And let's use our calculator, clear it from our previous calculation. We are working with pi multiplied by 0.02, square that, close the brackets, and that is going to give us our answer. Because it is a calculation within a calculation, don't round it off too far. So we're going to work with that value, 0.0125. 0.00125, and the measurement over there is meters squared. So once we've got our area, we can go and look at the rest of the calculations we need to do. They want to know from us what is the reading on the galvanometer. The galvanometer is going to indicate to us the EMF. So we are actually concerned with the epsilon, the EMF, which is going to be the number of turns multiplied by the change in the magnetic flux over the change in time. So that is the equation that we would be required to use over here. From that equation, you would see that we still need to go and find the magnetic flux. This is still unknown to us. So for us to go and find the magnetic flux over there, we first need to use this formula to go and determine it. Remember, B stands for the magnetic field strength and A for the area. The magnetic field strength from our text is given to us as 50 millitesla. We need to go and do a conversion over there. Remember that milli can also be written as times 10 to the power of -3 Tesla. All right, so that's what we're going to substitute in here. Can we just redo that? Okay, so what we're going to write here, we're going to start off with our 50 millitesla, or 50 times 10 to the power of negative 3, multiplied by the area which we just calculated, 0,00125. Right, let's bring up our calculator. So it is going to be the 50 millitesla times 10 to the power of negative 3 multiplied by the 0.00125 that we have from our previous calculation, and that is going to give us 1 over 16,000. Convert that into something that's easier to read. That is a very big number to work with. So what we're going to do is we're going to write it in scientific notation. We're going to move the comma back to between the 6 and the 2, so it moves back 1, 2, 3, 4, 5 spaces, and that would then be times 10 to the power of negative 5. So our answer over here, 6,25 times 10 to the power of negative 5 Tesla meters squared. Right. Now, this value needs to be substituted into that equation so that we can go and calculate the EMF as indicated on the galvanometer. So we're going to rewrite the formula we're working with. Epsilon is equal to the negative number of turns multiplied by the change in the magnetic flux over the change in time. Now remember, when we work with a change, it refers to the final minus the initial. They tell us that the number of turns were 80 if we go back to our text. The number of turns is indicated as 80 turns that we have on our coil, and they tell us that at the end the coil is far enough so that the field inside is 0. So our final strength is going to be 0, or the final magnetic flux will be 0. So to go and calculate over here the charge, it would be 0 minus the 6,25 times 10 to the power of minus 5 that we calculated from that one, divided by the change in time, and just have a squiz over there again. They tell us that the time is 0,2 seconds. If we type all of this into our calculator, we will find the following. Clear it from our previous calculation. It is negative 80 multiplied by 0 minus 6,25 is going to give us a negative 6.25 to the power of negative 5. Close your bracket and divide all of this by 0.2 equal to. That is going to give us our answer over there of 0,025, and the unit for EMF is volt, because that is an indication of potential difference. If they had stated that you need to write it in 2 decimals, then write there 2,5, 12 times 10 to the power of negative 2 volt. Right, so it moved in that direction, and that is where I get my negative 2 from. Let's move on to question number 5. Question number 5, we are now dealing with transformer. Remember that we have 2 types of transformer, a step up and a step down. If I have a step up transformer, it means that my secondary coil has got more turns on it than my primary coil. If I'm dealing with a step down transformer, my secondary coil would have fewer coils than my primary coil. So the difference between the two, we need to look out for that. The other way in which they would indicate it is that your primary coil has a higher potential difference than your secondary coil if it is a step down, or that your primary coil would have a lower potential difference than your secondary coil, and that would indicate a step up transformer. Let's deal with question number 5. They tell us that a transformer has 600 turns on the primary coil and 30 turns on the secondary coil. Immediately you would see over here that the number of turns for your primary coil is greater than the number of turns for your secondary coil. That is going to help us in answering question number 5. They want to know what type of transformer this is. Because we know that the primary is now greater than the secondary in terms of the number of coils, we know that this is therefore going to be a step-down transformer. In the event that they ask you to give a reason why you say it is a step-down transformer, you would indicate there that the number of turns have decreased from the primary towards the secondary coil. They tend to ask these questions for explanations to see your insight into the specific topic or into the section that deals with this question. 5.2. If 220 volts is now applied to the primary coil, what voltage would be provided to the secondary coil? We are going to use our transformer formula over here, where the potential difference of the primary coil over the potential difference for my secondary coil is equal to the ratio of the number of turns in my primary coil over the number of turns in my secondary coil. You have got all the information over here. They tell us that the number of turns for my primary coil is 600 turns. My secondary coil only has 30. So there we have got 300. For my secondary coil, it is 30. Sorry, let's just change that. That was 600. So that is our 600 turns. And they tell us that the potential difference across our primary coil is 220 volts. Just go and substitute each of those values into your calculation over here. We'll extend the page a bit. And we've got 220 volts over our unknown potential difference for the secondary coil. And over here we have our 600 divided by the 30. Because we are dealing with a fraction over here, or a relationship, it is easy to just go and cross multiply the different values in there to go and do our calculation. We would then see that our potential difference for the secondary coil is 600 times the potential difference is equal to the 220 over there multiplied by the 30. So to get rid of the 600 on this side, you divide by 600, and then your potential difference for the secondary coil would be on its own. And what you do on the one side, you must repeat on the second side, and we would work it from there. Take out your calculator, clear it from the previous calculation, and now we would say 220 volts multiplied by 30 turns divided by the 600 turns that we have in our primary coil, and that is going to give us a potential difference of 11. So there we go. That gives us 11 volts, and that is for our secondary coil. Question 6. A transformer with negligible power loss is connected to a 120 volt input. The primary coil has 600 turns, and the secondary coil has 15,000 turns. The secondary coil is connected to an external circuit which has a resistance of 2,8 times 10 to the power 5 ohm. I'm sure we'll use that value for a later calculation. 6.1 wants to know what is the potential difference that the secondary coil supplies to the circuit. This calculation is very similar to what we did previously. The potential difference for our primary coil, they told us that was 120 volt. The number of turns for your primary coil was given to you as 600 turns. For your secondary coil, it is going to be 15,000. Now from here we can see that our secondary coil is already a step-up transformer, which tells us that our secondary potential difference will be greater than our primary potential difference. You use that as a method to double check yourself to make sure that you do your calculation correctly. Substitute each of those values in. So we have 120 over the secondary potential difference is equal to, let's just change the formula so it is correct over there. That is the secondary coil, number of turns over there. So that was 600 divided by 15,000. So we have 600 times the secondary potential difference is equal to 120 multiplied by the 15,000. Divide by 600 over here, that cancels out the 600, and divide by 600 on this side. So we now have our secondary coil potential difference equal to 120 times 15,000 divided by 600. Put that into your calculator. Let's use brackets this time. 120 multiplied by the 15,000, close brackets, divided by your 600, and that is going to give you 3,000 volts. Remember, we said that this was a step-up transformer, so it has stepped it up from 120 volts all the way to 3,000 volts, thus increasing the potential difference. 6.2 asks us to go and calculate the current in this external circuit. They tell us that the secondary coil is connected to an external circuit and that there is a resistance of 2,8 times 10 to the power of negative, or to the power of 5. To go and calculate the current over here, you are going to use Ohm's law, whereby we look at the potential difference in the secondary circuit is equal to the current going through that circuit multiplied by the resistance. The potential difference we just calculated to be 3,000 volts. Your current is unknown and the resistance is given to us as 2,8 times 10 to the power of 5. Your current to the one side, that means that we have 3,000 volts over here divided by 2,8 times 10 to the power of 5. Work that through your calculator. Let's clear. 3,000 divided by 2.8 exponent 5. 3 over 280, and that works out to be 0,0107. A lot of zeros over there. So 0,0107. Going around that off, or you could write it in scientific notation, and that would be 1,07 times 10 to the power of 1 to negative 2, and the unit for your current over here is ampere. So not a very big current that we have passing through this component. Question 6, our penultimate question. Question 6.3. Now the power that is supplied by the transformer to the external circuit. When we deal with power, we are looking at the relationship between the current and the potential difference. Remember from our calculations that we did when we worked with electrical circuits, that as the current passes through the circuit, the energy that is delivered over there results in work that is done, and because there is a unit of time involved, we can go and calculate the power over there. So to calculate the power over here, power is the potential difference multiplied by the current. We are working with the secondary coil, so our potential difference over here is 3,000. We just calculated our current to be 1,07 times 10 to the power of negative 2 ampere. If we work that through our calculator, let's do an all clear. That is our 3,000 volts multiplied by the 1.07 to the power of negative 2. And that would give us the answer over there of 32,1 watt. Remember that watt is the unit of measurement that we use for power. That concludes question number 6. Let's look at question 7, which is a very nice question where we deal with a charged particle moving through a magnetic field. They tell us that an electron moves horizontally at a speed of 200 meters per second into a magnetic field with a strength of 0,5 Tesla that lies perpendicular to the motion of the electron. Remember that the word perpendicular over here means that they are moving at 90-degree angles with each other. 7.1. They want us to describe the motion of the electron on entering the magnetic field. As I said previously, the best way to describe anything is to have a picture in your mind. So if the electron is going to move horizontally in that direction, you can choose any horizontal direction as the direction which it moves, and your magnetic field is perpendicular, it means that your magnetic field would either be going in or coming out. Let's make our magnetic field coming out of the page for this explanation. So as the electron enters this magnetic field, it is going to experience a force which is going to push it out of the magnetic field. So it is going to deviate from a straight path. So to describe the motion over here, we would say the following. Upon entering the magnetic field, the electron experiences a force that pushes it out of the magnetic field. I think that would suffice for the answer for 7.1. There is no mark indication, but we have gone and we've explained to them exactly what is going to happen to the motion of the electron. It's going to enter the field, experience a force, and it is going to experience a change in direction. Let's deal with 7.2. 7.2 states that we need to go and calculate the force that is exerted on the electron. We are going to deal over here with the following formula. The force that is experienced by a charged particle is equal to the charge of the force, the charge of the particle, the velocity with which it moves, as well as the strength of the magnetic field through which it moves. Now, all of this information is given to us at the top over here. They tell us that we are moving with an electron. The charge of an electron is constant at negative 1,6 times 10 to the power of negative 19 Coulomb. However, for this calculation, we are going to work with magnitude only. Remember that. Very similar to working with Newton's, with Coulomb's law, where we work with charges and we work with the magnitude only. So the charge over here is 1,6 times 10 to the power of negative 19. The velocity is given to us as 200 meters per second, already in the correct SI unit, and the magnetic field strength over there is 0,5 Tesla. If we put all of that into our calculator, clear from our previous, that is 1.6 exponential value of negative 19 multiplied by 200 multiplied by 0.5. And that is going to give us our value over there of 1,6 times 10 to the exponential value of negative 17. And the unit of measurement for force is Newton. So you would see over here that the force experienced by the charged particle is not an extremely big force. Yet that force is strong enough to make the charged particle change its direction. And next year when we deal with electrical motors, you will notice that that force is enough to get a coil turning within a magnetic field. Just a reminder over there that it's more than one charged particle because you are dealing with several coils at one time that provides charged particles over there. That concludes the questions and the information on electromagnetism, concludes the session for me. I hope that this has been helpful to you, all of you, and that we will see each other again for the next show. Thank you very much. Till later. Bye-bye.